Taiwan University. Okay, and it's my pleasure to be the host of the 7th Consciousness Talks, I believe 7th, right? And we have 2 speakers today, Qianchen Liang and Dr. Chen. And our first speaker is Qianchen. And Qianchen is a graduate student in Nao's lab at Monash University. And she will talk about her research using massive report paradigm to try to answer how much information can be processed in a brief glance. And so I guess without further ado, let's please join me and welcome Qianchen. All right, Qianchen, it's all yours.
Okay, sorry, can you guys hear me?
Yeah.
No? Oh yeah, yes. Okay, I turned off one of the audio source. Hopefully that stopped the echoing. All right. I need to share screen and then share screen and put it over here. Now, can you also check on YouTube to make sure it's visible on YouTube as well? Because I'm doing multiple things at the same time. Not sure if everything's working. Can everyone see my slides?
Yes.
Take that as a yes. All right. Okay. Hello, everyone. Today I'll give a talk on our novel behavioral paradigm called massive report paradigm, which we use to review the truer informational capacity in our visual conscious experience. All right, so the first question is, at a glance, how much information do we get? Well, previous research goes back in the 1950s. They get an estimate of around 300 bits per second of information transfer for our visual experience. But our paradigm estimate around thousands. So why the difference? In today's talk, we'll talk about how the previous research do it and how we do it. So here's the outline of today's talk. For today, I'll start by explaining what do we mean by information for our study, and how do we apply this idea to visual experience. And then I'll talk about how these early research attempt to measure information in visual experience and what kind of limitations they have. And then I will talk about our own paradigm, and then I'll show the behavioral results and the estimated information transfer from those results. All right, what do we mean by information? A very commonly used definition in vision research is basically just the information is what we see, meaning the number of objects and visual details that we can capture at a given moment of time.
Wait, sorry, Qianchen, you probably need to turn on the sound again because there is some.
Can you hear anything?
Turned off. Maybe sound went off.
Oh my god. Okay.
Sounds fine on Zoom.
Yeah, Zoom is fine because it's using a different mic.
All right.
Okay. So do I start over? I'll continue from here, I guess. I think it has to do with the fact that I'm presenting and also doing the stream, and result in either echoing or not having any sound. Okay, I'll continue from here. So commonly used definition is, how many things we see at a glance. And based on this definition, it's basically the more things we can see at the moment, the more information we get. If we accept this definition, let's consider this photo. For each and every one of us, the only kind of information we get is a panda. And because panda is black and white, even if you're colorblind, you still get the same information. But does this really mean that everyone get the same amount of information from a photo? That doesn't sound right? So instead of focusing on, this panda itself, let's think about what we can distinguish this panda from. For us, with some common sense knowledge of animals, the moment we see this panda, we immediately know that this panda is not a tiger, it's not a parrot, it's not a dog, it's not a lot of animals. However, for some kind of panda expert or like a huge fan of pandas, in addition to all these animals, this fan also know that this panda is not a lot of particular pandas. So they all have their own names. So now we can see that compared to us, this panda fan has a different internal representation of this panda photo here. And this idea of differentiation is actually consistent with the mathematical definition of information by Chen, proposed in 1948, which is how much information an event carries is defined by the number of possible alternatives there are. And based on this theory, each binary discrimination, which is to discriminate between two things, gives you one bit of information. So when we look back at this example of like pandas and other animals and other pandas, when we successfully discriminate between panda and a tiger, that gives us one bit. And then discriminate between the panda and the cat, another bit. And then with elephant, another bit. So that's like 3 bits. And there are some previous research back in the 1950s that attempt to measure the information using some behavioral paradigm. For example, here, a study by Clemmer and Frick in 1953, they used this kind of abstract stimulus of this kind of 4-dot formations in a 3x3 matrix. In their study, they show the participant this kind of formation for 30 milliseconds. And then after this formation disappears, they ask the participant to mark out where the dots are on a 3x3 kind of matrix answer sheet. And typically for this kind of 3x3 matrix in their study, each position, there are only 2 possibilities. 1, the dot is present, and 2, the dot is absent. So that's one binary discrimination. And that gives you 1 bit of information per position if the participant kind of was correct about whether a dot was present or absent in that position. And if they successfully recreate the entire formation that was presented, then that means they were correct in all 9 positions, and that gives you 9 bits. So successfully recreating this formation gives you 9 bits divided by the presentation time of 30 milliseconds, and that's 300 bits per second. So that was a very neat and nicely controlled kind of method, but there are also limitations. The first limitation is that using this kind of abstract stimuli, the number of alternatives are really, really limited. For this 3x3 matrix here, right? This position, because you only have 2 alternatives, there's only 1 binary discrimination. But when we think about what we see in everyday life, for example, let's look at this scene. For this 1 position over here, we notice that the kind of discrimination we can make is way beyond just we see something which is present or don't see something which is absent. Instead, we know that this position, what we see in this position, is different from many, many things that we did not see. And that corresponds to a massive number of discriminations. And using this kind of abstract stimuli, this kind of massive discrimination space cannot be captured. So you're going to ask, okay, so if there's a massive number of comparisons here, how about we show a stimulus to a participant and then ask her to report all the things she did not see in one position, and then we move on to next position, and so on and so forth. But just think about how many things we can report. That would be extremely tedious and nearly impossible. So how can we address the limitations in the previous studies in a rather clever way? So here we'll introduce our task. Sorry. So we mentioned that abstract stimuli do not mimic the way we differentiate between visual experiences in everyday life. So a simple solution is to use natural scene images then, which mimics what we see. And this is what our task looks like. In a trial of our task, we present a natural scene image for 133 milliseconds, and then we mask the image, and then we ask the participant to judge each of 6 small image patches, like these here, on whether these patches was part of the original image or not. And among the 6 patches, there are 3 patches that were from the image, and there are 3 images that, there are 3 patches that were not from the images, which were we randomly selected from a different image set. And for this task, we recruited 240 online participants to do it. And each participant will be tested on 34 images. And here's how we allocate the images. Overall, we have 133 natural scene images. We divide this set into 4 groups of 34 images. And we allocate each group to 60 participants. So in this way, we also get each image to be tested on 60 participants. And moving on, we talk about how we can make massive number of comparisons, but then asking one participant to report all of them would be nearly impossible. Here's a better solution. So look at this comparison here. I'm sure that all of us can easily tell that what's in this position is different from here, and maybe a lot more things that we can agree on. So let's think about this. Instead of asking one participant to report everything that he or she did not see from this position, how about we get many participants to view this image, and then each participant just report on 3 absent things. So participant 1 report on these 3 things, and then participant 2 on these 3, and then participant 3 on this, and so on and so forth. And if this kind of intersubject consistency is right, then we can actually collapse across all participants' responses as if it was responded to by one participant. And this is exactly what we did in our task. For this image, we have 60 participants. While all the present patches are the same for all the participants, the absent patches are different across subjects. And if we agree that intersubject consistency is correct, then we can collapse across 60 participants and to create kind of hypothetical single observer, as if this hypothetical observer view this image and respond to 3 present patches and 180 absent patches. All right, so here's a summary of my task. In a trial, we present a natural scene image, and then we ask the participant to judge 3 present patches and 3 absent patches. And then the absent patches are not repeated across subjects. And here's the result. Here we plotted the percentage of present judgments that participants gave to the present and absent patches. And you can see that they're extremely good at discriminating what's present and absent in a briefly presented image. Now that we have the behavioral data, how do we use them to calculate the information transfer? Let's start from a single pair of a present and absent. In a single pair, because it's a discrimination between two things. That's a binary discrimination. If the participant could do it perfectly, that gives us 1 bit of information. And to calculate the actual information transfer, we need to incorporate their actual discrimination accuracy. So here we use the responses to the present and absent patch in this pair, and then we calculate the discrimination accuracy, which ranges from 0 to 1, with 0.5 being chance and then 1 being perfect discriminability. And we just incorporate this accuracy into the information transfer so that the information transfer for this pair will range between 0 to 1 bit. And then assuming that each present and absent comparison is independent from each other, we repeat the same procedure on all the possible pairs of this present patch with the rest of the absent patches. So that would be 180 pairs, each with 0 to 1 bit. And then additionally, let's assume the other present patch, present and absent pairs are also independent from each other. We repeat the same procedure on the rest of the 2 present patches and each calculate the information transfer. And then we sum all the information transfer together and divide that by the presentation time of 0.133 second, and then we get the information transfer for the current image. So maximum would be 3 present patches times 180 bits, because there are 180 absent patches, and then divided by the presentation time. And maximum, that would be 4060 bits per second for an image. And here's our result. Again, we plotted the information transfer for our 163 images in here. And this is the previous estimate. We can see that we get an information transfer that's way higher than the previous estimate. On average, information transfer rate for each image was around 3000 bits per second. And for your reference, here's the information rate of other modalities. For discussion, from a study, we know that a brief glance is highly informative, accumulating to around 3000 bits per second of information transfer. And note that this information transfer was estimated from 60 participants, each responding to 3 absent patches for 1 image. We can easily imagine that if we increase the number of participants and increase the number of absent patches, we can the estimate would also increase as well. So in a sense, our current estimate may only serve as a lower bound for the actual information capacity for a visual experience. And there are some remaining questions. So I talked about how this estimate will continue to increase as we increase the number of participants. But is there a limit to this capacity? And if so, how can we find them? And another question is that, looking back at our results, we can see a huge variability across images, ranging from around 2000 to 4000. So what kind of features in those images that are accounting this variability? We'll be addressing these questions in our upcoming paper, so yeah, stay tuned. All right, that's it. Thank you very much. How can I escape? Oh, yeah.
All right, thank you, Qianchen, for your interest in research. And we're now open for questions and discussions. So all kinds of questions and comments are welcome.
I've got a question.
Yes, please.
Yes.
Cool. So it's super interesting. I've been looking forward to seeing these results for a while. So I guess my question is really about like your predictions, or maybe just to clarify, yeah, what your hypotheses might be, because it seems as though the upper limit, as you mentioned at the end, of this information transfer is really just set by the amount of participants you use and by the amount of comparisons you make. So if you increase the amount of, was this, section absent stimuli, then presumably the transfer rate would continue to increase. So do you think there is an upper bound on this information rate that you will expect to get towards? Because if not, then like an argument could be that you're not really capturing information in the initial glimpse. You're adding information every time you show a comparative image. And so by adding more and more images, you increase the information kind of comparison, but not the information that was in the initial glimpse. So I guess that's a confusing question, but yeah, do you think there's an upper limit, and how much is that upper limit set by the initial glimpse versus the inclusion of the comparisons?
Okay, so let me rephrase your question. So your question is, if I continue to add absent stimuli for the participants to judge, of course it's going to increase. Of course it's going to increase almost in an unlimited way. So what is the upper limit anyways, in a sense, right?
Yeah,
and my answer is that our ability to differentiate what we see and what we don't is actually limited. And it depends on what that absent stimuli looks like. So in our actual experiment, there's one part of things that we actually left out for this talk for simplicity, is that in addition to this randomly, like the absent patches that we randomly selected from a different image set, we also included one patch in which they were modified from the original image patch. We modified by changing the object inside, but then the overall structure remained very similar. And when we used this kind of patch, we found that the participants were just, very bad at discriminating between these kind of very similar stimuli. And I guess that would account for the limit of their capacity.
Right. So this kind of suggests, though, that, yeah, you're increasing the amount of information by using very different comparison images in your absent classes, which suggests maybe that there's not an infinite amount of information in the initial glimpse, but this upper bound is really set by these comparisons. So I guess, yeah, to me that introduces a wrinkle, because it suggests that you can just increase this information flow or information rate by using certain types of comparisons, but if the comparisons aren't right, then the information flow, drops quite a bit. So yeah, I guess I'm a little bit unsure about whether or not this shows there's an enormous amount of information in the image or just in the comparisons which you introduced. But anyway, I think it's just semantics, and I'll look forward to the paper.
Wait, Matt, just one thing to add to your comment. Mostly, it's totally fine. But one thing that is something probably Qianchen wanted to add was that the information is additive.
Yeah.
Okay, so if you include these kind of non-discriminable kind of patch, it doesn't decrease the information. So something that is discriminable adds more and more of this, information transfer estimate up until this capacity limit. So that's why we are talking about through our bound or through our estimate of the information transfer rate. So if we include this kind of threshold-like thing, then it's appear to saturate really quickly, but it's because we didn't test something that is actually discriminable.
Yeah. I think there's still a wrinkle there with like adding information that wasn't in the original image, but by performing this comparison, you are kind of like artificially inflating the amount of information in the first glimpse, because you could say, for example, like you could just play someone an auditory tone and say, did you think of this when you saw this image? And of course they're going to say no, but does that mean that the amount of visual information in the first glimpse is also increasing because you're showing them and comparing them auditory stuff? Like, I don't know if that's a reasonable thing to say. I guess, I'll read the paper with interest, but It's a really cool paradigm anyway. I think it's definitely going to raise a lot of questions, and it should be really exciting to see when it comes out.
Qianchen, did you want to answer or?
I'm not an expert in, the relations between memory and conscious experience in real time, but a very kind of oversimplified answer I would offer to this kind of question is that without the initial input, without the initial input, you can't really say, no, I didn't see it, right? Eventually, you still rely on the initial input.
Yeah, I agree. So I guess another way of thinking about it is like, is this information that's available in the initial input or information that's available to generate with infinite comparisons you could make based on your memory? I think they're two different things, right? Because when you see a glimpse of an image, you're not making thousands of comparisons at the same time. But anyway, yeah.
Yes. So the kind of discriminability we are trying to say here, it's not like we see this and then we kind of consciously telling ourselves, this is not a panda, this is not a tiger, this is not a lion. It's not like that. What we are trying to address here is that this experience itself sits among a massive relationship with all the alternative experience that one already has. And then as soon as you have it, it already is distinguished from the other experiences. If that makes sense, yeah.
No, that makes sense. And I understand kind of, the theoretical background of why this is interesting, for sure. But I'll take up enough time. I'll let other people ask questions.
Okay, thank you.
All
right, so it seems that there are a few questions in the chat that's related. And I actually have a very similar question. I guess it's the same questions. Well, the question, I guess, is for discrimination tasks like this, it seems that participants can have very few information coming in. And along the way of information processing, they'll fill in information, including all kinds of filling in and retrieving information from memory and all kinds of stuff. So I'm just curious, this paradigm, is it possible that, you are actually capturing this later part of the information processing that's actually filled in, but not actually from the bottom up of true information? Well, I guess, these are the similar questions in the chat as well.
Yes, so I think I can also address that question with what we did right here. So just looking at these present and absent here, they are different enough for us to, just make that decision with the initial kind of very limited input. And fill-in only comes into effect when it comes to what particular object did I see. So fill-in is only able to fill in with like these kind of small details and not necessarily up to the point where I didn't see anything, but then almost anything, but I filled in the entire image in my head, if that makes sense. How can I explain this? So for example, in this image, like in this situation here, in our study, we sometimes show this image with the object that's consistent with the context. And then we ask them, did you see this object, the original one, or did you see this replaced one? And sometimes we show the image with this, incongruent object in the image, and then we test them the same question. And what we found was that while participants are generally not very good at discriminating between these two anyways, regardless of what object in there, they tend to endorse what's consistent with the context, and they tend to reject what's not consistent, regardless of what's in there. And that's the kind of level of filling in, the level of impact filling in has in this kind of task. Does that answer your question?
Brown, you might be muted or not. Did it make sense, Brown?
Well, I still have other questions, but I guess I'll let other people ask first. Andrew, you just raised your hand.
Yeah,
Please.
cheers. Super interesting. This is really, really fascinating. I guess my question's not so much, I don't think it's an issue for the study that you've actually run. And I wonder if it actually suggests that in some ways, you're ending up with a conservative estimation of the amount of information here. So at the start, you sort of mentioned or alluded to high-level perception. So some people, when they look at a panda, will just see a panda. But people who are experts in pandas might see, oh no, that's not just a panda, that's this particular species of panda. And that happens to be a panda named Bob or whatever. I wonder if you could say a bit, or if you've thought a bit about how that sort of, that idea relates to this intersubjective, what was it? Intersubjective
consistency.
That's the one. So not everyone is going to be experts in pandas, right? So I'm wondering if the intersubjective, the mashing together of people, having the massive paradigm that you've got, sort of rules out or ignores a lot of additional information of this high-level perception stuff.
Yes. So Andrew's questions was that taking from my initial example of this common people versus panda fan, it kind of already shows that there isn't intersubject consistency doesn't always work because we and the panda fan are different. So my answer to that is that our level of task is to judge something of what they see and discriminate from something that's completely irrelevant. So analogously, it would be something around a panda versus other animals. But yeah, occasionally there would be patches that are actually very similar, and then people that some people cannot discriminate at a point and some other can. So I guess to continue to verify that, yeah, we will do experiments to see to what degree intersubjective consistency is kind of a true thing. Yes.
I think it's a totally reasonable assumption. It's gonna, I don't know how you're gonna get around it, but I guess my thought is just, you might actually be underestimating the amount of information that's in some people's perceptions because they have all this high-level stuff.
Yeah, definitely. We can say that's like expert perception.
Yeah.
I think that's a kind of area of research where experts in a certain field, they perform differently in certain visual paradigms. But probably the current image set doesn't apply to that, but yeah.
Probably.
But if you use like animal images, then yeah, probably.
Cool, super interesting, thanks.
It's also interesting kind of thought. I guess, it's worth trying actually, really, if it really differs between some kind of population of experts versus novice, or even like, some kind of a psychiatric population, like autistic or, schizophrenic and things like that. That might also relate to Brown's question of how much of the memory or top-down kind of process affects on this estimate, right?
Yeah.
Great. So I'll ask one more questions if that's okay. So
you are the chair.
So imagine that we're looking at this picture, right? This bowling picture. Now imagine that I only get the gist of it. I know that this is a man playing bowling. Now I don't know how much information that gist is, but imagine that the only thing I get is this gist. Then using this gist, I should be able to reject all the pictures on the right-hand side, right? So my question is, well, is it possible that actually when people are processing the image, they only get some gist? And this gist probably doesn't have a lot of information in there. But with this information, they can infer and use it for many things, including rejecting all the images on the right, because none of these images looks like that's someone playing bowling. So if that's the case, well, is it possible that you're over estimating the amount of information they're getting?
So my response to that would be, okay, so I will rephrase the question. So Brown's question is that we only need, so let's say we only take a glance of this image and then we get only a very rough kind of gist of this image. And then with that gist, we are already able to reject all these absent stimuli here. And if in that sense, if we are able to use a gist to reject all those, are we overestimating the information capacity? My answer to that would be, it really doesn't matter how detailed they see in the initial image. What we care is just how much they can discriminate. If they are able to use gist to discriminate between this many things, then that's their capacity itself. And I think that's what gist does as well, right? It summarizes the visual features in a certain area of the scene, and then it gives you an impression, and it also helps you to kind of exclude a lot of possibility that it is not, right?
Well, then I guess, then the key difference is that, are you claiming that this is information coming bottom up in a glance, or is this information that people can use later in the stage for all kinds of discrimination tasks, right? Yes. So I guess, the finding is the finding. I guess, the interpretation could be different if you think of it differently.
Yeah, I can ask question like just very similar like Brian said, like I think different, you use it's a different type of the pictures. My people have different strategies to process. For example, this picture, a man playing bowling. This is a very clear meaning. Like we just extracted the abstract meaning of the picture. That's enough. But for some other picture, like there's no clear meaning, like just some shape or color. I think face this different type of features, man. People might have different strategies, or and that might like affect the amount of information like you get.
So your question is
like just like
depending on the stimuli.
Yeah, depend yeah. I mean, it's like not just exactly depend on stimuli. Like some stimuli you have like clear like a meaning, like a man playing bowling, right? When people see this picture, they just need to get that's the most important information, and that's all. People might just ignore the background; they don't care about background information. But if there's no like clear meaning, like with like the green picture, just like some color and shape things, and they can't easily get the meaning. Like they just like process some like deep like bottom up information like color, shape things. So this is the really difference, I think, maybe like for people to process this different kind of things.
Kind of our kind of stance on this or understanding of information is that even we see something like a complete black screen, and that is extremely informative because we are able to easily know that, you know, this black screen is not a lot of things. Because yeah, I'm not sure if that makes sense.
Yeah, so just to help a little bit for both Brown and also, you know, yeah, as Qianchen said in the end, you know, in our framework, black uniform thing, which is not, you know, describable anything else other than, you know, black uniform, that's, you know, as informative as others, because most likely that is highly discriminable from others, right? And that's our definition of information, and which is consistent with the information defined by the Shannon. And that's basically, you know, how we are defining it. And so, you know, you're concerned about the meaning, and also gist is valid thing. But however, we are saying that, you know, in the case of the gist, what is the amount of the information in the gist, right? Or what is the information in the meaning, simple description of man in the bowling? If there is thousands or millions of possible kinds of description, and you are choosing one out of this million, then that's a huge information, right? So that's another way to think about the same thing. And clearly from our end, man in the bowling is definitely not sufficient to discriminate the patch on the top right, for example, right? Top right doesn't have, like there is a little bit of the kind of left hand, a little bit you can see, but that's not sufficient to say that this is coming from man in the bowling, right? If we are testing on the board part, then it could be, but it's not on this top right part. So meaning or gist cannot account for our results. That's another way to answer the same thing. Make sense? All right, Brown?
Yeah, I'm fine for now. So,
yeah.
So time-wise, do we have time now, or should we move on?
Yeah, maybe we should move on. Or
okay.
If you have any more questions, maybe we can take.
We can ask it later, right?
Yeah.
Okay, so shall we move on to the next talk?
Okay.
Okay, so thank you, Qianchen, again for your interesting talk. So our next speaker is Chen. So Dr. Chen is a professor in the Department of Psychology and Behavioral Sciences at Zhejiang University in China. And his research interests include visual attention, working memory, and consciousness. And in today's talk, he will talk about his work on attribute amnesia. And in the same time, I think, well, he will try to address the debate of phenomenology overflow. So again, without further ado, please join me and welcome Dr. Chen.
Okay, is that clear, my sound?
Yes.
Yeah.
Okay. Thank you, Now and Qianchen for organizing this session, and thank you, Brown, for chairing. And today I will share you some of my recent work about attribute amnesia. So attribute amnesia is a phenomenon that was discovered by my colleague Brad Weibel in Penn State University and me. And I think this phenomenon is highly related to the philosophical and scientific debate regarding the nature of consciousness. That's why I want to share this work in the conscious section. The philosophical debate is about whether our visual consciousness is rich or sparse. This is a really hot topic recently in the field of consciousness. And the debate arises because of the gap or the conflict between our daily experience and the scientific findings. For example, in daily life, whenever we open our eyes, and many people believe they will experience every information in front of their eyes. So it seems like they have a rich and detailed visual world representation. But on the other hand, many studies suggest that the amount of information available to report is very limited. Like, for example, like our visual working memory capacity is only 3 to 4, right? So clearly there's a huge gap between what we experience and what we can report. And this dissociation leads to a scientific debate. That is, do we see more than we can report? On the one hand, many people will believe, yes, we can see more than we can report. And this is usually called overflow argument. And the key evidence supporting this argument comes from the well-known effect of iconic memory and its violations. But on the other hand, like many people will say, okay, no, we can only consciously experience what we are able to report. This is called a no overflow argument. And according to this argument, they believe like people can only conscious experience of information under the focus of attention, for example, here. And all the information outside the attention focus will be blurred. And this kind of information will not reach consciousness. But the question is, how can we explain the rich experience belief in our daily life? And they explain this is just one type of illusion, because our attention was continuous scanning of the environment. That's why we have a feeling we have a rich world. And the key evidence support that no overflow argument comes from the inattention blindness and the change blindness. And this aware-no phenomena, these two phenomena together suggest without attention, people even fail to notice obvious information, for example, a gorilla, or changes like, for example, people substitution. So this phenomenon suggests that people cannot consciously perceive information outside the focus of attention. So in summary, all previous studies about they try to address the overflow debate by testing whether consciousness can be experienced outside the attention focus and overflow's reportability. But unlike this previous study focused on unattended information, the attribute mission study that we are introducing the following sought to address this debate from a new perspective by testing whether those fully attended information, of course, we will use clearly visible information, whether this kind of information is necessarily reportable. If we could demonstrate even fully attended information is not be able to be reported in some cases, then we can demonstrate attention overflow report. We can provide strong evidence for overflow, right? And this is the logic leads to the attribute emission studies. Okay, let me introduce what is attribute emission. Here I will present one example of attribute emission experiment. In a typical experiment, we will show participants 4 stimuli, one target letter among 3 distracted digits. And the stimuli will present briefly, and which will be quickly masked. And the participant's task was just to find the target letter and report its location by clicking a corresponding key. And the participants needed to complete a couple of different trials. And then in a surprise trial, we unexpectedly asked participants to report the identity and the color of the target letter before the location report. After the surprise trial, participants will receive 4 more control trials, which were exactly the same as the surprise trial, with the only exception that in these control trials, participants have an expectation that they might need to remember and report identity and color information. And that's the only difference between surprise and control. So for the whole experiment, participants will complete 155 pre-surprise trials and 1 single surprise trial and 4 more control trials. And that's the design of the typical attribute emission experiment. Okay, let's see the result. In the pre-surprise trials, participants' performance in reporting the location of the target is pretty great, which means they can easily locate the target and report its location. Critically, the results in the surprise trial shows that people even fail to report the color and or identity of the target letter because there are 4 alternative choices for them to choose, and the chance level is 25%. So their accuracy is quite close to chance. Importantly, their performance increased significantly in control trials, and there's a huge significant difference between them. So we call this phenomena attribute emission, we call AH effect. The most important findings in AA is the identity. The identity is a task relevant information that participants have to pay attention to. They have to use this information to locate the target. So we call this key feature. And the participants even fail to report the key feature that was fully attended. So that's the most important and the most interesting findings in attribute emission. And this is a very robust phenomenon. We replicate this phenomenon with different kind of stimuli, different kind of paradigms. For example, we set the target as an animal like a snake. We set the target as a negative emotion, and we set the target as a Chinese poem. And we replicate this phenomenon in all these kind of stimulus. And until now, there are more than 10 papers about attribute emission published from our lab and the other labs in the world. So this is a very robust phenomenon. And we think attribute emission suggests even attended information could still overflow report, for example, the key feature, right? But if we want to support overflow, we have to demonstrate this attended but unreportable key feature had reached the consciousness, right? And this is the key point, right? So some people might argue, right, in our attribute emission study, participants might only unconsciously perceive the key feature because of the short stimuli duration or because the visual interference from the mask or distractors. And that makes sense, right? And we run a couple of experiments to rule out these possibilities. For example, in an experiment, we increase the stimuli durations and remove masks. In another case, we set the key feature as a pop-out color, and we still replicate attribute emission. And in another case, even more interesting, like we ask participants to track the ball and for a long time, like for example, for 5 to 49 seconds, and then we surprise ask them to report the color of the single color ball that they had just tracked for a while. And we still found 30% of participants fail to report the color of the ball, which is significantly worse than the control trials. So this finding suggests like, or rule out this possibility, like people just unconsciously perceive the key feature because of the short duration or interference. But another possibility might also argue like people might locate the target by categorization, but without identifying the key feature. For example, in a classical experiment, participants might just categorize, okay, this is a letter, not a digit, and then they can find the target and report its location, but without necessarily identify what is the letter, right? And that is a make sense argument. And we also rule out this possibility by presenting only one single stimulus at the center of the screen, and ask participants to judge the parity of the digit, for example, is order or even number. And we still replicate attribute emission. Participants still fail to report the meaning of the number in a surprise trial, even in a single stimulus case. And this experiment was even replicated in a real world context. Now, in another case, we use complex and meaningful stimuli, for example, Chinese poem. And in this task, there's no way for them to perform the task based on categorization, because participants have to extract the abstract meaning of the sentence to perform the task. We still replicate the attribute emission. So we also remove this possibility. We demonstrate participants still fail to report the attended key feature, even when they have to consciously access the information. So this result suggests conscious information is not equal to report. Conscious information overflow report, right? The key feature information already reached the consciousness, but the participants still fail to report. But the question is why it happens? Why it happens? Why conscious overflow report? And we have run a couple of different experiments. And for example, in a case, we combined a paradigm with a working memory-driven attention capture paradigm. And this effect is one characteristic of working memory. And we found key feature could not produce working memory-driven attention capture effect, which suggests the key feature was not stored in working memory. And in another case, we calculate participants' working memory capacity when they simultaneously perform AA experiment. And we found the key feature did not occupy a working memory capacity like random items. And in another case, we use EEG, like we advantage the CDA component, which is a classical index of working memory load. And we found the key feature could not elicit the CDA component, which means they did not store the key feature in working memory. And in another case, we demonstrate A was nearly eliminated once the key feature was forced to consolidate into working memory. So all this experiments together provide converging evidence that consciousness is not equal to working memory. Working memory, the information stored working memory can be reportable, but the information already enriched consciousness is not necessarily stored in working memory. So we demonstrate consciousness overflow report. And that's the take-home message. And we found people fail to report information that had just enriched consciousness. So this means reportability might not always be suitable as an index of consciousness. Conscious awareness is not sufficient for working memory, at least in the attribute emission case, right? And this results reveal novel and strong evidence for overflow. And this is a reference of some reference about attribute emission studies. And I want to thank you, my collaborators in my lab and its findings. Thank you.
Okay, thank you, Hui, for your nice talk. So we're now open to questions and discussions.
There's some chat question.
Yes,
Brown.
so I saw that Ariel has questions.
Yeah, I'll go for it. Yeah, that was super fascinating and quite convincing. I'm just curious if you ever ran an experiment where, or at least I didn't quite, so maybe you explained it and I didn't catch it in the methods. But it seemed to me that normally you were running experiments where you use the same set of stimuli, so colored letters or poems or those sorts of things. I'm wondering if you ever ran a version of the experiment where you had completely different stimuli that were like very different for each individual trial to rule out memory interference effects between trials having an effect, and whether you still see, if you have done that, whether you still see attribute amnesia under those circumstances.
Okay, this is really great questions. Like, yes, we did that. And we, in one experiment, we set, like, we use different type of letters in different trials. Means the target will never repeat across different trials. And we still found attribute emission. But in another case, like we use animal. Like this experiment was also run by another lab from Australia. They published that paper. And both of us found when we use animal pictures, if the target was always different animals in different tribes, the attribute emission was largely reduced. So it depends on the different type of stimulus, right? And we explained that, like, for the letters, those similar are very familiar. And we are very familiar, even if they are different in different trials, they are still might like some interference, like you said. But for animals, like different type of animals, they are not familiar enough. We can find the attribute emission was largely reduced. Yeah, that's a really good question. Like there's some in the trial interference, to produce attribute emission, but that's not the whole story, because we still find in some case, like for example, attribute emission was still observed even when the surprise question was on the first trial, and we still found attribute emission.
Oh, that's fascinating. Thanks.
Yeah.
All right, so wait, now?
Yeah.
Questions?
All right. Yeah, I'll ask question. So it's related to Ariel's, but the interference that you are talking is related to this concept of prospective interference, right?
Yeah.
I
Yes.
imagine.
Yes.
Yeah. So that means that the target can be also a distractor in other trials. And
Yes.
because you need to kind of disentangle this confusing target and distribute distractor across the trials, you need to inhibit unwanted information, right? So my question is that you actually towards the end went to address the question of why this attribute amnesia happens, but I'm thinking that maybe there is an effect of this active forgetting going on always, because
Yes.
each trial you are supposed not to remember this irrelevant features, right?
Yes, exactly.
Yeah, so it's that I'm thinking what's the best way to test this hypothesis, like
Yes.
after you use that information consciously to locate the target, you try to forget it as quickly as possible. Do you have any idea How to
Yes,
test
that's great questions. Like,
Oh.
yeah, actually we run that project and we have a paper under review. It's just about that. And that's exactly what we are, I totally agree with you. Like, that is exactly what we are thinking about attribute emission. Like, we think people actively inhibit the key feature because the key feature is the information that is no longer useful in the future, right? But that information already received high activation because it was appended, because it was task relevant to perform task. So such kind of information will produce interference for your future task. So we need to like actively inhibit that things, right? And that's our hypothesis. And in another like project, I just told you, like, we run an experiment by compare the key feature with another case, like completely task irrelevant feature. Like complete task irrelevant feature, like this the information people need to, like they only need to ignore, they don't need to pay attention to. And in that case, we compare these two conditions and we found people have stronger memory representation for completely task irrelevant information in comparison with the key feature. Like that means like we actually inhibit the key feature and we have even weaker working memory representation compared than the completely irrelevant feature. And in the two cases, all the stimuli are exactly the same. The only difference is instructions. I'm sorry, I didn't prepare that case. Like maybe I can show you the paradigm. Okay, okay. Oh, sorry.
Can I ask a quick question?
Yeah, give me a second. Let me just show that paradigm.
Oh, sorry.
I'm sorry, maybe not here. Yeah, I see. Sorry. Let me check. Yeah, it's here.
I don't know, you may be sharing only the PowerPoint. We don't see it.
Okay.
You may need to
Okay, I can
unshare.
PowerPoint. Yeah.
Oh yeah, or copy.
Okay.
Yeah.
I can copy it.
All right.
Okay. Okay, can you see the paradigm?
Yeah, now I can.
For example, in this case, we present like one triangle. And in one case, we just ask people to remember the color and ignore the shape. So in this case, shape is a completely irrelevant feature, right? And in another case, we set the shape as a key feature. For example, we ask participants to judge whether this is a circle or not. If this is not a circle, remember the color. So here they need to use the shape to judge whether this is a circle. But their task is also to remember the color and report the color. So then in these two cases, we can set the shape as a key feature and set the shape as a completely task irrelevant feature. And all the stimuli are exactly the same, right? Then we can find like when the shape is a task irrelevant feature, we demonstrate that people, this irrelevant feature trigger like a working memory guide attention effect, which means people automatically store irrelevant information in working memory. And that was not a surprise because some previous study also found that. The key point is like you can see the key feature was not produce this kind of effect. And there's a significant difference between them. So to this, we can demonstrate, okay, people actively inhibit the key feature.
Yeah, that's great. And yeah, I was thinking, you know, while you are answering to my question, maybe like this kind of, you know, priming, negative priming kind of thing can address these things and so on. Yeah, so that makes a lot of sense. And I think, yeah, this also relates to probably inattentional amnesia as well in the classic.
Yes, exactly. Like inattentional amnesia proposed by Jamie Wall. Like,
yeah, exactly.
Yes, yes.
All right. Eric has some question.
Yes, I sent it to the chat. It's sorry if I missed that in the discussion, but I was wondering whether attribute amnesia, which is, by the way, very interesting and very convincing topic that I didn't know. Thank you very much for the presentation. I was wondering whether it's a kind of stable phenomenon. By stable, I mean, is it something that is kind of fixed in us, or it's something that we can see evolve over time, especially under the influence of things like education, training, and things like that, basically? Thank you very much.
Can I reframe your question? You see means whether attribute amnesia was influenced by education or training? Is that right?
Yes.
Okay. We haven't like studied that, but we have run like a child experiment about attribute amnesia, and we really found like interesting finding. Like we found like children like almost have no attribute amnesia.
Oh, I was going to
it seems like a phenomenon. Like it seems like children can remember, can have better memories than adults, right? And that's like it makes sense if we really think about the detailed mechanisms, because just like Noah said, like we think attribute amnesia reflect we actively inhibit some information which require like executive function, right? And because children have like poor executive function compared with adults, so that's why they cannot inhibit the key feature. So yeah, this might be some related with your question about education. So. Right.
Yeah, I was actually going to ask an exact question like that, because there has been a couple of papers saying that children has, when they need to attend and also remember one feature, then they remember everything together with that, right? Even though everything else is irrelevant. And the adults actually inhibits that. That's from Takeo Watanabe's lab and another lab from, you know, excellent, great.
Yes. But I think it's still slightly different. In their case, they said like children automatically distribute attention to all features of the whole object, even if the feature is test irrelevant, right? They talk about it is because of the attention distribution. But here, you know, in our case, the key feature is the information they have to pay attention to. So it's not about attention distribution, it's about inhibition. So this, I think the mechanism is different. Right.
And also related to that, I think it would be very interesting to test it on autism population as well, which is also known to have limited ability to be selective about incoming information.
Yeah, that's our plan. And one of my PhD students are running a plan to run that project, but we still haven't started that yet. Yeah.
I see. And that also addresses Eric's question, right? So, you know, if you become autistic afterwards, for some reason, I don't know, with the brain change and so on, then it might change this attribute amnesia over the time as well. Like earlier, I also wanted to ask whether this attribute amnesia in children, was it already published or?
No, we're still writing that paper. Like, hopefully, I will share you the guys like when it come out.
Yeah, excellent.
Hey, so I have a question. So it seems that one of your assumptions of attribute amnesia is that the participants are fully attending to the target, right?
Yeah.
But I'm wondering, well, if it is possible that actually the participants are only partially attending to certain features, let's say location. And let's say, for example, maybe they're using some kind of visual statistics analysis, right? They can see there's a difference between digits and alphabets. And now they use that to log on to the location, but they're not actually fully attending to other features like colors and shape.
Yes.
Now, if this is the case, then the attribute amnesia is actually more like inattentional amnesia. So I'm wondering if you have any control experiments to test this possibility.
Yes, I think maybe this experiment can answer your question like here, right? We run an experiment, we present only one single digit at the center of screen and with no mask, and we ask participants to judge the parity of the digit. And then we surprise ask them, what's the digit you just saw? So we didn't only ask them color, we asked them the meaning of the digit that they have to use to perform the parity task, right? So we don't think it's inattentional emission because they have to pay attention to the identity of the digit for the parity task.
I see.
Yeah.
Wait, so for this task, they're actually reporting whether this is an odd or even number, or?
Yeah, odd or even number.
Okay.
By the way, so all of these are like, inattentional blindness, that you set up the expectation that some of the features are irrelevant in the end, right?
Yeah.
So how many trials are necessary to set up the expectation? You used like 150, yeah. Is it possible to induce this in a couple of trials?
Yeah, that's really great questions. Like we found that in some case, yeah. First, I want to claim like the attribute emission will influenced by the number of pre-specified trials in some cases, like, yeah. But this is not necessary. For example, in a case we found like in 2015, the first attribute emission study, we found we only run like 11 pre-specified trials and we found attribute emission. And in another case, we found even on the first supply trial, when the supply test was put on the first trial of the whole experiment, we still found attribute emission. So it's not necessary, but the number of pre-specified will influence the magnitude of the effect.
Wait, first trial, really? So you are explained about the task structure, and then you have probably did a practice or something, right? No?
I guess in that experiment, I think maybe if practice just 1 to 2 trials, we want to control that number of trials. I forgot exactly like details whether we have tried, whether we have included some practice, but I think even we include just 1 or 2 trials because we want to control the number of trials.
And that was in the first of the paper.
Yeah, and we can say, and in that paper we published in like memory cognition, you can say attribute emission decrease as they increase the number of pre-specified trials, but it was still there even on the first trial.
I see.
Yeah.
And a very kind of minor question, just regarding this study where you use Chinese poems, what are the key features that you are using? And
okay. Sorry. Yeah, that's the Chinese poem. Like we have like this 4 Chinese like poem sentence. They represent different topics, different theme of the meaning. Like for example, some of us, one is like about love, and one is about just like the friendship. And we ask them to report, to find the sentence with different topics as the 3 and the other 3. And that's the key feature. Like the abstract meaning of the sentence, that's the key feature.
And the pre-surprise trial,
they just report the location of that sentence, and then in the surprise we give them 4 different type of Chinese poem sentence, and they all contain the same meaning, the same like topic, not same meaning, same topic, and they still cannot find the target. Okay.
Thanks.
So we have another question. Zefon, please go ahead and ask the question, please.
Yeah, I apologize that I cannot open my camera, but thank you, Professor Chen, for the interesting talk. I really like attribute amnesia. So my question is like, so it seems that all the experiments that you have done here are conducted on the visual modality. So what about auditory or tactile modality? Like, other sensory modalities that a human have? Like, have you guys ever explored like whether attributed amnesia could be generalized to other sensory modalities? And also, for example, like for each participant, that you have only tried like one surprise attribute, like you after several pre-surprise, and you just ask them one surprise attribute. So what about like after this surprise attribute, you put more trials, and then you got a different surprise attribute that you didn't ask before. It's just more rounds of surprise tasks. That's like, for example, attributed amnesia could occur to one subject more than one time.
Okay, thank you for the question. For the first question, yes, like when we another lab, not us, they published a paper, attribute emission in the audio domain, and they still found the attribute emission. So I don't remember, it's like in Melville condition or some, like I forgot the journal, but you can find that it's already published. And for the second question,
thank you.
Yeah, and for the second questions, yes, we run that project. Like we add like we run exactly the same experiment like you just mentioned. Like we add like multiple different surprise question. Like for example, on the first surprise question, we ask them to report the color, and then we ask them to report location, maybe like 15 tries or more. And after that, we add another second surprise question wherein we ask them to report identity. So the two surprise questions, they test two different type of features. Even in that case, we still find there are almost no attribute emission in the second surprise trial, which means like once people have an expectation, you might test them. You cannot cheat them again. Like people are really smart. Like.
Oh.
Okay, thank you.
Yeah.
That's very interesting.
That's surprising to me because I was going to also ask about this in relation to the finding that also again Jeremy Wolf reported in Nature a couple of years ago. Do you know that Jeremy Wolf did the visual search experiment with a realistic, stimuli like airport security?
Yeah.
Yeah, and then when the gun is there, then that's a sort of a target kind of stimulus, right?
Yes.
And then when the proportion of the trials that this target is there is lower, like lower than 5% or something like that, then people almost always just miss it.
Yes.
Right.
Yes.
So in that case, people know that it's not like every trials. There's no target. Every once in 20 trials, they know that that's going to be asked, but they can't just adjust the criterion optimally.
Yes, exactly.
So I was thinking that maybe if you ask this attribute amnesia every 20 trials or like 5% of a trial, you may find attribute amnesia. But you say that from the second time, they don't.
Okay. Yes. Okay, that's really great question. Like yes, exactly. Like. In attentional blindness field, like Emily Ward and Brian Shaw, they published a paper they call it like repeatedly in attentional blindness. Like people will experience in attentional blindness multiple times. Yeah, in that case, because like people pay no attention to the unexpected stimuli. But in our case, it's different. Like the key feature is the information under the focus of attention. That's the key difference between attention blindness and attribute omission. Yeah, I think that might be the reason. But I agree with you. Like because we only insert 15 trials requiring them to report location. Maybe that's not long enough. Like in another project, we haven't finished that because we just the initial evidence. We ask participants to just we don't ask them spark question. We just ask them spark question, and then we use some other paradigm to probe their memory representation of the key feature, and we ask them to run multiple blockers, maybe 200 or 300 trials, and we probe their memory representation of the key feature. the result initially show that there's some decrease. Yeah, there's some decrease, but I guess they still can able to report the key feature. At least the accuracy will significantly higher than on the first spiral trial. Yeah, so it might decrease, but just a little bit, I think.
I see.
Yeah.
Okay.
Another question from a different perspective is that I was wondering whether you knew or you've made studies tracking some profile of the participants. In particular, whether some participants have heavy experience in meditation or with things like psychedelics or things like that. The reason for this question is because apparently some studies explain that can show that there is a link between meditation, psychedelics, and things like that with the state of consciousness. Okay, and so I may be saying something incorrect here, but it's meditation, psychedelics, and so on have put in some cases apparently would put in a state more like what a children is basically. Okay, especially from the perspective of perception. Okay, and so that links to the study about children. Okay, I was wondering whether you were working with adults with such kind of training, okay, with meditation or experience with the psychedelics, okay, and to see whether this has an impact on the results and on the study of attribute amnesia. Thank you.
Okay, thank you for the question. No, we haven't tried that. We haven't training do some training to we run some project that we use schizophrenia participants and autism participants, but we haven't tried to do some training like you just said. We haven't tried that. Yeah, but what's the logic? Why you think you train what? Train executive function or?
So it's more to see about the effect of. So there are some models models of the brain that talk about the brain as a filter.
Yeah.
Okay,
yeah.
But there are other studies that show that if there are filters, okay, if we can isolate those filters, these filters evolve over time, okay, and they evolve because as we grow, I mean it's a physiological aspect, okay. So the difference perhaps between a child and an adult, okay, but also education and training and the kind of specialization we get. Are we more a library rat or are we more an athlete? Okay, and these apparently affect the work with the plasticity of the brain to create different kinds of filters. Okay, and so it's more about so attribute amnesia as a concept looks pretty coupled with such kind of filter approach to seeing the brain. And so my question is about is it related, and can it tell us more about attribute amnesia and about these so-called filters?
I see. Thank you. Thank you.
Thank you.
Okay, so due to our time limitations, so we'll have to end it here. So please join me in thank our two speakers, Qianchen and Hui. And so now do you want to say anything or announce anything before we close it?
Yeah, so thank you, Brown, for hosting this week, and we are always, welcoming different speakers or topics in the future. And the next one we are planning is going to be October 1st, I think, and that's going to be about dream and sleep and consciousness. And then 2 weeks after that, October 14th, we'll have a session on pain. Your colleague Debbie and NU philosopher Colin are going to be the speaker at that time. Yeah. With that, thank you.
Okay.
Yeah. Thanks a lot. Bye bye.
Thank you. Bye bye.
Thank you for your.
Thank you.
Perfect.